strong interaction. As I said just now, strong interaction involve baryon number. Just like a weak interaction involve lepton, or of course lepton number. So just the quantum numbers that are conserved is baryon number. So quark have baryon number of plus 1/3, anti-quark all have baryon number of minus 1/3, and lepton, sometimes lepton involve also in strong interaction, have baryon number of 0. And later we will prove this. In general, baryons consist of 3 quark. So meaning antibaryon has 3 antiquark. So B become 1/3 plus 1/3 plus 1/3 is become 1. And antibaryon is obviously antiquark, antiquark, antiquark. B value minus 1. And mesons consists of quark antiquark pair, so baryon number is 0. So this baryon, meson, of course you have so this consists the baryon, antibaryon and mesons form what you call hadrons. Of course you have anti-meson, but then you have to put Q1, Q bar 2. So anti-meson actually you can put here Q1 bar Q2. Okay, just to be consistent. So the bar is not it is distinguishable. Okay. Now, there is what you call a basic vertex or vertices. So this is in the Feynman diagram, or in this case, because it involves quark, what you call quark line diagram. So that is just quark interacting with a quark through. So there are many possible interaction of involving quark. For EM interaction involving quark, it is through the mediation of gamma or photon. If it is weak, W plus minus and Z. And in strong interaction, it is the gluon that play an important role. So in this strong interaction, we will deal mainly with the gluon. But quark diagram are not the only one. There is another one here, which is antiquark and antiquark, and this involves the same gamma W plus minus Z0 G, and of course you can also have a quark antiquark pair generated from various gauge boson. So you will see that conservation of a baryon number provides stability. Example, a proton cannot decay into a E plus into a photon like this, or it cannot decay into a E plus pi 0, for example. Okay? Even though kinetically this is allowed. Why? Because those on the right has less mass than on the left. Okay, but they don't decay like that. They are conserving, what you call it, with conservation of charge and so on. The reason being, nothing on the right are baryon. Okay. Now, let's look a little bit more detail. There is another thing about this quark. First, quarks are given in flavor. Or what you call type. So you have up, down, strings, charm, bottom, top. Okay. Of course, later we will see that there is some flavor mixing. Just like a kaon system, there is a mixing of CP states. Okay, between the kaon to give the long and short give kaon. Yeah? So here there will be a flavor mixing. So this later we will go into detail given by CKM matrix. For the moment, assume they are different. All observed hadron, meaning this meson baryon, are colorless. Why is that? Because you can consider this is due to the so this is the observation, but you can consider the gauge boson for strong interaction, the gluon. which can be considered as just like it is a kind of a color charge with color anti-color pair. So the gluon can be considered as a color anti-color pair. We will go into that detail later, but because of this, because of this, it can transfer color charges to the quark. So the quark are colored as well. So this give quarks color as well. Just to give you an example, meson, which are Q bar, quark anti-quark pair. So because observations say that hadrons are colorless, you don't measure any color in this or color charge in this hadron. So this implies that meson they must have R, red anti-red, blue anti-blue, and G anti-G to be colorless. So these are the color combination of the meson. Okay. Because it is quark anti-quark pair. How about the baryon? Baryon are also colorless. So how do you sort of figure out? How do you figure out to make it colorless? It is not like meson where you have green anti-green, so that becomes zero, no color. In quark, in a baryon, they are all quark. So how do you do that? So for the baryon, which are quark, you have RGB minus RBG plus BRG minus BGR plus GBR minus GRB. So this combination make it colorless also. Now there is another very important observation apart from all hadron are colorless. That is the fact that experiments show that quark, anti-quark, and gluon have never been observed as free particles. And gluon have never been seen as a free particle. So this is actually later give you the real meaning of strong interaction. So strong, the quark are being confined by the gluon, sehingga no quark can come out from the individual meson or baryon. So they are never seen as free particle. So the quark and anti-quark are confined within. So this leads to the idea of confinement, okay, of quarks. By this I mean also anti-kuat. Okay. Of course, later, towards the end of the course, when we discuss about the relation of high energy physics with cosmology, the early universe and so on, we will show that at very high temperature in the early universe, this quark can come out actually, because the temperature is so high that nothing is confined, and you have free quark, what you call the quark gluon soup. Jadi macam sup. Dia tidak jadi apa ni yang panggil atau berbola daging. Tak, dalam bahasa Indonesia dia panggil apa? Bakso. Bakso. Bakso tu sendiri pecah dan dia menjadi sup tu sendiri. Betul. Jadi hadron dengan meson tu kamu anggap bakso lah. Tapi lepas dipanaskan terlalu tinggi, bakso sendiri jadi sup, dia hancur. Dan dia menjadi kuat gluon sup. Sedap tu kalau tapi panas lah. Now, in terms of the theory, actually, we don't go into the detail, the Lagrangian and so on. Later I will just show you the Lagrangian and how it is solved, especially bila kita membincangkan tentang Higgs boson. So for the moment, so the theory of strong interaction actually is quantum chromodynamic because of this color. So this chromo comes from the color charge that is being carried by the gluon. So in say if you have an electron here, electron plus here, if they are both near to each other, there will be a electric field, or rather not exactly, the electric field is actually created through the photon field. So these are photon. Actually charge ini, macam mana elektron positron dikenal ataupun bercakap antara satu dengan lain, atau dalam arti lain merasai antara satu dengan lain melalui photon. What you call a photon field. Macam manusia ni dia ada medan yang gaib lah, kita tak tahu. Orang kata kalau ada medan ini, maknanya itu yang boleh orang kata sehidup semati tu kan. Sebab ada charge antara positif dan negatif ni. Begitulah. Begitu juga dengan elektron positron. So the photon field is the one. But now if you have a quark and anti-quark here, anti-quark and a quark here, dia pun ada interaction juga, but the field is very tightly because of the gluon. So the gluon are very strong field. And then this in photon you rarely see a self interaction. Photon rarely or very weakly self interact. That's why dia dengan dia agak jauh. Medan foton dengan foton-foton lain jauh. Yang gluon ni, gluon are strongly self-interacting. Strongly self-interacting. Suka berinteraksi antara diri dia. What happened was this gluon, say 3 gluon, they self-interact. Of course, later, one of the idea of trying to understand gluon is for dalam pelanggaran proton-antiproton to create hadrons. So this is exactly what experiment is being done. Proton collide with antiproton to give you cascade of hadron. So this is the early experiment to understand meson and baryon formation by proton-antiproton collision in the high energy experiment. So you have production of hadron. So one of the things that they look is the a small third jet. So this is a two-jet experiment, but there is a possible third jet. They are looking the formation of a glue ball. So so far, the energy in the Large Hadron Collider does not reach high enough energy to produce glue ball. But people believe during Big Bang, not only kuat gluon soup, but glue ball are also produced. Ni yang kita kata bakso tadi. Glue ball ada bakso. Anyway, so because of this phenomena, very strong interaction, self-interaction of the gluon, we can assume that the potential of gluon field VR is roughly about lambda r. So this leads to confinement. In fact, one of the early model on this gluon, meson and baryon model is the MIT back model. You can go to the internet to look for this. We are not going to discuss the MIT back model. Apa yang diceritakan oleh MIT back model probably ialah you boleh duduk dalam bag dan you boleh bergerak dalam bag, tapi you tak boleh keluar dari bag. So basically, you have a bag inside and 3 quarks inside here. If you go to high energy, the bag becomes bigger, and one ball there, one ball there, one ball there, trying to come out. The bag can get bigger, but they can never, the ball or the quark can never get out. They are just confined. Macam masukkan orang dalam guni lah. Dia merenta-renta nak keluar, tapi dia tetap berada dalam guni. So we don't go into detail yet for this gluon field, except that we go back to the existence of some of these quantum numbers. Later I will later we will construct what we call how to construct the meson and the baryon from some of these fundamental property of the kuat. So let's go back to some early experiment involving strong interaction. So the first experiment was in determining this baryon number and how it comes about. So nombor berapa ni? Tak ada nombor 6 kan? So Heisenberg 1932 suggests that proton and neutron are different state of same particle. So he basically he created idea of isospin. So what is it that so this isospin has I1, I2, I3 component, and according to him, where the third component is different, plus half, this is for proton, and for minus half, this is neutron. And then, actually, he is the first one who proposed the idea that the charge is related to the baryon number divided by 2 plus I3. So he is actually the first one to relate charge with baryon number and isospin. Later, of course, when it becomes generalized to other quantum numbers involving strangeness, charmness, and so on, those are the Gell-Mann-Nishijima idea. So because it involves charges, so this first initial formula were meant to describe mainly EM interaction. Later, when Gell-Mann and Nishijima extend this formula to include charmness, strangeness, quantum number, and so on, then only it become extended to strong interaction, or what you call QCD, whereas EM is QED, quantum electrodynamic. So the fact that this formula fits both EM and strong interaction was because the structure of QCD follow almost the same structure or analogy with the QED. So that one we cannot go into detail, but so the first observation was in experiment for this proof that isospin is conserved is in deuteron interaction. Where the third component was found to be 0, 0, 0, 0. So 0 equal to 0. But then